So I told the GSEC that I'm more than happy to introduce myself. And most of you know me wearing various hats for the center at Columbia. So my name is Tian Zheng. I'm a professor of statistics, and often I enjoy labeling myself as applied statistician, data scientist who play in everybody's backyard. A famous saying about statistics is that the best thing about being a statistician is you get to play in everyone's backyard. And then I definitely take that, to my heart. So my work at LEAP, in addition to help with the organization of research education integration and try to shepherd certain activity forward, is I also enjoy developing some statistical projects motivated by the important work that we're doing here. So today I'm going to share a ongoing project where we are looking at the distributions of dynamic systems and then try to see what we can do using statistical thinking. And so I'm preaching to the choir here that the Earth system, the climate system is a dynamical system with closed loop feedback, right? So if you take the entire climate system, including the universe, right? So that is a closed loop feedback. There's nothing coming in and goes out, right? Like we know the whole thing is a closed loop feedback system, and then they actually is coupled, they interact with each other. And that is also the reason why our climate system model, the Earth system model, are being simulated using such a structure that you can have dynamic locally organized into the grid cells. And then by the end, we often call them the balancing, the using the energy, check for energy balance. Those are feedbacks, right? You are trying to use the governing equations or the physical laws, try to provide feedback to the dynamic system locally. So, so currently that when we apply machine learning to climate projection, this slide summarizes the status quo, right? So status quo for the most low-hanging fruit that we're seeing a lot of fruitful progress at LEAP is that we do a lot of long runs of simulations, and then we hope to connect those simulations of climate system model with data, talking about how we can modernize data assimilation using machine learning, how we can use machine learning to generate reliable uncertainty quantification, and then whether machine learning offer opportunities on tuning the models in terms of reasoning about initial values, parameter, boundary conditions. And more importantly is that if we have untraditional data, such as satellite images or human behaviors or some extreme events, how can we use them as a way of evaluating models in terms of metrics where machine learning can offer an opportunity. So here, the state of art machine learning applied in this field, we have heard a lot about replacing numerical PD solvers using machine learning surrogate emulators. And then this, sorry, I should use this for the online folks. This is seeing a lot of latent space, reduced order models are seeing a lot of traction over the past few years, because the motivation is that even the climate system with the high resolution grid is a highly super high dimensional model, but from the observable dynamic behavior of this model, you believe, due to the smoothness of it, you believe there is a low dimensional representation that can be discovered and which could help with both computational efficiency and model reliability. So that is why we look for reduced order models. And then the third is where is in our name, and then learning Earth with AI and physics, that we're trying to put more effort of integrating into ML. And this project is in particular hoping to offer a alternative answer to that. And the progress there is that many people are using hybrid loss. There are efforts using transfer learning. There are efforts using Bayesian approach. Happy to chat with anyone who's interested in this. And then I think, and I think there are a lot of interesting paper in this field. And then the last is using, we are seeing a generative AI and diffusion model for downscaling, not just for downscaling purpose. In the past, downscaling used to be a you have the low resolution climate projections, and you try to downscale to the point where you need to answer a question. Here, think about downscaling is also an opportunity for model development, right? If you cannot have this connection between the climate model and observable data, then how do you know you're doing the right thing? So therefore, when you figure out how to use machine learning to downscale to the level where observation take place, those generative AI and diffusion model are highly differentiable. So they create a differentiable programming backward bridge into the model that can actually allow observable data to provide insight, provide information usable by the model. So that's why this is one of the most exciting thing we're thinking for the renewal. And I think I also is another place where I will be more than happy to discuss further. So for this talk, I want to go down to a very, very simplified vision of dynamical systems and then see what we're trying to address here. So the simplest way to think about the dynamic system we need to deal with in real life is that we are looking at some kind of Y of interest, and you believe that there is a resolved equation for Y, how that equation works, which could include other forcing factors, other inputs, neighboring points. So this R represents resolved and U represent unresolved, and F include other forcing external to the system. So typically, in a lot of climate Earth system model, climate system models, that you know there's things that are unresolved, but you hope that those unresolved part is ignorable if you choose the right resolution. If you go to smaller, the unresolved equation, it can be ignored. Therefore, you're using primarily the resolved one to create numerical emulator, or you replace the unresolved with something that is like a simulation based, such as the LES or the large eddy simulators, and then the cloud resolved models. Those things are trying to help with the unresolved part of the equation. But most of the time, and from my observation, is that people are doing this, right? So they are, let's just pretend that a machine learning researcher come in and says, what you're trying to solve, where we have this very high dimensional partial differential equation or ordinary differential equations. We're using numerical solvers. We try to propel in time, and it's super, super slow, and then we want it to be faster. And the machine learning researcher will say, sounds like a modeling problem, predictive modeling. Basically, you're trying to create a Y hat. Like machine learning people will say, you're getting a Y hat. You have training data. You spend all this computation power getting the training data. Y hat equal to F of YT plus F, right? Like if I see this, just to me, this is just another nonlinear function that need to be estimated, and then machine learning is very good at estimating that nonlinear function. So this is basically a lot of papers that follow the same storyline, that you have a system, you have the training data prepared using numerical simulations, and the machine learning comes in, fit a surrogate model, and then generate Y hat, and then you evaluate Y hat against the ground truth, which was the one simulated. So if you look at this closely, that the work we give to the machine learning workflow is learn this delta t, learn how the system works between y to between t to t plus delta t. So that's a highly local, highly short term, and often local, because we often just give the machine learning algorithms a local cell, saying in this we have an equation, it's solved numerically, it generates the next time point and then fit to it. And then so I was thinking about this line, and I read a very interesting paper from Climate System where they did a experiment. They evaluated a few models, a feed forward, our favorite feed forward artificial neural network. Like we have seen this a lot in papers. And they also evaluated something called reservoir computing echo state network, which consider, I think, temporal dependence, and also another model called recurrent neural network, LSTM, which is also famous for their ability of learning temporal So therefore that they saw that both sets of model, the A and N, have no memory, just do propelling, where the other two models consider history, so should be able to take into account the temporal dependence, long-term memory of the system. They both do equally well for short-term prediction. So if you calculate mean square error for the instantaneous prediction, they're on par to each other. They are basically the same performance. Then, but they say but the other two model that considers temporal dependence, they say reproduces long-term probability distribution of the system even after losing track of the trajectories. And I found that this sentence to be very interesting for two reasons. One is often when you see a machine learning algorithm lose track of the trajectories, you will label that as a failure. Fair? Right? When you calculate mean square error, 1 day forward, 2 day forward, one time step forward, 2 time step forward, 10, like you see the MSE exploding, which means that you lose track of the trajectories. Understandable, because you're dealing with nearly chaotic system. You shouldn't expect that anything with an arrow would be able to stay up with the trajectory. That will be a myth, in my opinion. Like, you know, that will shake the core of me as an applied mathematician, like formal applied math major, to know that there's something that can be that predictable. But on the other hand, it says that it failed to track the trajectory, but still offers something useful, which is the long-term probability distribution, which is the general behavior of the system that can still be useful in climate projection, because by the end of the day, we don't care about today's temperature 20 years from today, but we worry about the risk of having an extreme cold or extreme hot day. And that is a distributional question rather than a trajectory question. We don't need to know every day's temperature from today to 20 years from today, but we would like to know what the overall distribution will be like, right? So we just quickly go over, we see that in the Clemson paper as well, like you get offline performance, good performance. When you plug in, you'll see a systematic drift and sometimes instability observed. So something says to me as a statistician, like the information machine learning was picking up locally in a short time period locally is not the same as the information that can allow us to predict distribution in the long term. Something is interesting. On one hand, certain models were able to do that. They're picking up something from the data that is not in the instantaneous short-term dependence structure that machine learning try to fit the F. And then on the other hand, that if we don't consider that, we're gonna run into trouble when we replace parts of the big model using just machine learning emulators. So there are talk about how do we integrate this, and you can run a very long run and try to model that, and then people argue that is counterproductive. For the same time, you run those long run to feed into a data hungry machine learning framework. You may just as well run those simulation and call it a day. However, some people are generating, so can we use short terms? Can we make assumptions? And then so my question here is, if we create a hybrid loss to learn F, the loss will be on how to improve F, and then improve our emulation of the system where the P is like a feedback to the system, where the machine learning, by the way we set up the losses, is assuming that the error is IID random errors, but in reality that you're observing the behavior of a dynamical system where the feedback is not random, is not independent. It's try to sustain the system overall distribution. Does that make sense? So the machine learning by design assumes y plus f of x plus epsilon. That epsilon is assumed to be independent IID. That's why you use mean square error. Yes, that's why you use the. But in reality, the system you're trying to model, the error is neither independent or identically distributed, right? And then worse for a feedback loop is it statistic deal with dependence all the time, but we are not well designed to deal with where the epsilon is responding to the mean responses. We usually don't make that assumption, and that is, I think, true for dynamical systems. So here for a tour example that we basically generated a very simple linear dynamical system that Y is being propelled by a matrix A, and we designed A to have eigenvalue close to 1 so that the system is rather unstable, often lead to exploding values. And then we create training data using the same transition A, but make the noise a little bit different. So therefore, if the RID, right? So we say we create two systems, one system for the training, one system for the testing, and they have exact same A matrix. So the machine learning will be able to recover the A matrix pretty reliably, but the system driven by both the main linear projection and then the arrow terms will develop very different trajectories. More important, very different stationary distributions, because the station distribution of the system depend on both A and sigma, the covariance matrix. So then we make life easier. We create a univariate response to visualization reason, which is the length of the vector. So you can see that this is actually something I feel like a lot of people already observe in their research already, is that the x-axis is the true y, the y-axis is the predicted one. You can see that it more or less traces but it comes short. So in distribution wise, that you can see the blue is the overall distribution of the distribution of the predicted y, where the orange color is the true y, where we assume we have some side knowledge of the true overall distribution. I will show you why. We can make an assumption later that we use that to calibrate. We're not using that to train the model. We use that to say the model is capturing A accurately, but it's not capturing the arrow distribution accurately. So the blue comes short of the truth. We can, by knowing the yellow knowledge distribution, we use a existing strategy in statistics to calibrate each of the predicted value, and then create a distribution much closer to that. And we didn't do, it's different from quantile matching. You can say you can sort the observation, do quantile matching. We tried that, it didn't work. And what we did is using something called kernelized Stein distribution calibration, which is based on a distribution measure between a sample of point and a distribution, and you were able to write something similar to a likelihood function, but not a likelihood function, is a score, kernelized score, comparing a sample point with distribution, and that score is differentiable so that you can calculate the derivative of that score against each of the individual point, and then that create a gradient that's suggesting that if you move individual observation a little bit, and those will lower the score. The lower the score, the closer they are. So that is what we decide to use. We choose to use it. We choose to use it because the KSD is connected with other distribution measure in the literature. No matter which one is your favorite, you can see a connection. And it's a generalization of a Fisher divergence under a radial-based function kernel. And then it can be viewed as a special case of MMD, which is a popular with machine learning based on distribution. The most importantly is that it allows for straightforward calculation of discrepancy between a sample observation and knowledge distribution without any of integration optimization, because speed is very important to us. So this is what it looked like, and mathematically, it is it's kind of a correlation, kernelized correlation between correlation between the the score function of known and then the actual distribution generate the sample. So that's the mathematical definition. Then using something called U statistics that this has been simplified to this form just to show you that the math is there, and I'm not gonna dive into there because we don't have a lot of time. I just want to show you what happened to that. So the workflow goes like this. You have the training input X, you have training predicted Y, so you try to build this. So you build a point-wise predictive model and using whatever your favorite training loss, mean square error or median absolute error, and just train that. So then then this model is here, your favorite model. Input X goes through the model, give you the predicted Y, which is raw Y, and then we create a kernelized calibration, not improving the model, but improving the predicted Y hat directly. And this does require additional information. That additional information is called knowledge distribution Y, so we will find it somewhere. And then we have the calibrated Y tilde. And then this is our proposed workflow. And to evaluate the proposed workflow, that we will look at the evaluated predicted Y without. We generate evaluation data independent of the training data, the testing data. And then we generate the raw predictions Y hat, and then we calibrate it just as we propose we will do. Then we will evaluate using distribution loss and then point-wise loss, right? We want to see the performance in point-wise predictions, distributed prediction, and then calibrated, and then calibrate distribution loss, calibrate point-wise loss. So we naturally, because it's our framework, we would expect that the distribution loss will definitely improve because you bring the distribution closer. And then we were not 100% sure whether we'll be seeing the point-wise improvement. It's not guaranteed. It's only guaranteed if the distribution calibration is improving the point prediction. There is a connection between the two. So we apply to Gillen's PCO data of the test bed. And then we all know most of us here know the story that the real data is very, very sparse, only cover 1 or 2% of the global ocean. Then there is an effort of using indirect observation, try to help with the actual population. And we replicated this current state-of-the-art model in the literature that partition the ocean into regions using self-organized map, and then using the available input variable to predict the PCO2. So here we reproduce a whole workflow. We also borrowed idea from the paper from Gillen's group of we don't have ground truths here, and then we use the test bed in the following way. So I'm just gonna jump to here that we will pretend one of the member of the test bed being the Earth, and then one member of the test bed being model. We believe in reality. When we apply to real data, we will do extrapolation for the real Earth, where the knowledge distribution need to come from somewhere, but the knowledge distribution will not be available for the entire reconstructed actual population. So the knowledge distribution need to come from somewhere. So here, for the evaluation purpose, we assume the knowledge distribution is coming from another member of the test bed. So if we only use that member for the distribution, we don't take any local data from it. So to show you that this is the knowledge distribution for one of the months over the years, and you can see that even though you see a shift of values, but there are certain similarities from year to year. And then we applied that. We were able to show that the calibration does improve the distribution, as you can see on this graph. But more interestingly is that It also improved the mean square error rather dramatically, which means that is when the machine learning trying to do the extrapolation using the input, it will not do anything to balance across the ocean, where the overall distribution from the system model take into, for example, the total physics of the ocean that will construct the distribution, because you cannot just be any value. There are governing equations of the process. And then we see this across all the months that we're observing that, of course, for the months that have a lot of observations that the model is doing well. For the month that you don't have a lot of observations, that the biases, the mean square error, exhibit different level of biases. For example, the October, November are extremely hard to predict. And that's where you see that the calibration really help. So we see the same improvement in distribution learning as expected. And then so to summarize, I'm happy to talk more about the technical detail of this framework, and also what we can try next. Basically, that we're thinking out of the box of try to improve machine learning predictions, not by improving the instantaneous prediction, but rather try to have the prediction being informed by distribution knowledge could be available for the learning task. Okay, thank you. 30.
I know we're right up at time, but is there one quick question or one or two quick questions?
Thank you for the presentation. I think you've mentioned in the beginning the possibility of using generative models for the instantaneous prediction. Have you tried the experiments of this form and try if this can improve the long-term distribution?
So we haven't. So for this particular project, we haven't talked about generative AI, but I believe that for generative AI to respect physics, you could even consider where the physics knowledge can come into the framework. Currently, that the physics a lot of time is on the temporal dependent. People try to use like attention mechanism, try to allow the machine learning model to pick up the dependence in the system due to physics. However, I feel that the control, the inter-system control may not come naturally only from the temporal dependence. So that's why I feel some of the stationary distribution, if I remember my PDE courses, one thing is that, the stationary behavior of the system is actually quite a very impressive feature of dynamical system. I feel that is also where what is the definition of a physical system, that even though you see instantaneous chaotic behaviors and the certain distributional behavior emerge as a long-term behavior of the system. That's what the climate projection is actually betting on. If the distribution is not predictable, then I don't think our projection can be reliably estimated. So the generative AI for downscaling is not currently looking at distribution because it's more to the point. But in the future, when this expands for more full coverage downscaling, I think this work will be relevant.
Thank you.
Okay.
Yeah, so thanks, John. Looking forward to discussing this more. But so one of the things about PCO2 in the ocean is that there's this very strong seasonality, and if you define that, I can see that your model would improve. One of the things we're really interested in is the long-term trends, which are in fact a smaller signal, right? And I think that's probably true in many things. So how much is your method dependent on just improving, like basically, is it just giving us a better seasonal cycle versus really capturing that trend over time? And is there something in there that to just decompose those pieces?
Right. So the seasonality is definitely one of our concerns. That's why we're collaborating only use the knowledge distribution of that month rather than pull everything together. So we are doing month by month to bypass the seasonality problem. We follow exactly the setup of the SOM FFN framework by using the feed forward neural network using these inputs. So we're making the same assumption. We tried the day of the year as an input. I don't think it improved the MSE, but we definitely think that the assumption here is the relation between the SST, all this with the PCO2 is a physical relation that like the change is not changing the relation, that the change is changing, say the temperature or changing the some of the dynamics that drive PCO2. So hopefully that machine learning learn the relation between the two, and then the relation between the two can reveal the long-term trend rather than capturing the mechanism driving the long-term change. I think that's my take from this setup, but definitely I think we could consider any machine learning algorithm that can account for system shift, which is a systematic shifts. Even that, I still believe the calibration can be the one step forward. Right, so in a way that if you think about this plot, that imagine that this is what the model says, right? This is what the model says that the PCO2 distribution from the model should distribute going forward. Imagine that this simulate beyond 2016 all the way to 2050, right? So that distribution. So the machine learning model studies will extrapolate based on this relation, which we believe is a connection between the observable data and the unobservable ground truth. And then the distribution projected by the climate system model can help us calibrate the machine learning prediction to the knowledge distribution.